So if you see in the last, especially I've been, the list of collaborators have been really increasing. So it started with, of course I had my own students, but Satoshi was one person who really triggered, is it clear? So who really triggered a lot of developments which we could achieve, and this team we formed and we wrote a couple of interesting papers. Then Vivek is here, he is now in his final year, and now I have another young student who is now in the third year, Shashwati, she is also here. So this is the main students, postdoc who are the main drive, and then the second list you can see they are the Russian collaborators, and this started out with an Indo-Russian project in 2014, and we have a lot of interesting results from this, and we are currently updating from time to time in a naughty book website. Okay? And I think this was like a 5-year plan with Keshav. We started in 2012 when I visited McGill, where we wanted to understand a very hidden paper, or I should say that very, very dense paper of Witten, where he seems to get a clarity on what this polynomials mean, and I think we've still not dug enough to, I'm still not confident. I wish we go further and further into the depth to understand that. So the clarity in calculations still don't have, but there is some clarity on how that picture is related to Oguri-Waffa picture. So this is the work with Keshav, Radu, and his Keshav student Veronica. Okay? So I will briefly touch upon this. So the plan is to give some kind of what is the current status on the polynomial. Mainly the drive is to solve the classification problem, and I'll explain what that problem is. Okay? So that's the outline is what is classification problem. Then I will just briefly take you on a tour to well-known polynomials from knot theory. So one of the thing is like mutation or mutant knots, we do see all these well-known polynomials do not distinguish them, even though they are different knots. And I'll give a brief review of Chern-Simons from Chern-Simons method to get the knot polynomials, and focus on only the process of mutation operation. Is it detectable from Chern-Simons theory? And then all these polynomials, the coefficients are all, it's a Laurent series with coefficients which are integer. So the drive in the last 15-16 years has been on trying to get a meaning to these integer coefficients. What does it mean? So one is Oguri-Waffa picture following the topological string duality conjecture of Gomar-Waffa, and later on there is one more grading added to it, and this was done by Schwarz-Gurkov-Waffa, especially in the topological string context to understand why these are turning out to be integers. There's an independent mathematical work which is the categorification method introduced by Kono, and this is especially like a homological chain complex, which is bigraded, and they can argue that the dimension of such a vector space will be these integer coefficients. The third approach has been trying to reconcile what these people have been saying in the topological string context. So they have an intersecting brane approach which was introduced by Witten in 2011, where he tries to argue that these integers can be accounted as solutions to some elliptic equations. The number of such solutions are these coefficient, integer coefficients. Okay? So in some sense, these integer coefficients have become meaningful. Like whenever you give an integer, you should either account it by as number of BPS states. If it is positive integers, definitely BPS states. dimension of a vector space, or it should be like number of solutions to a differential equation. If you can give such an accountability, then we are convinced that these polynomial integers have some meaning. Okay. So this is the outline, and I'll go very slowly with lot of pictures and explaining, and also the steps. Go to the board and explain if required, but please stop me. Idea is to see the pleasure of some of these things which we are trying to uncover. And we still are in this, and we are still trying to see whether there is some calculations which can be done from here to explain them. So these are still an open question. Okay? Am I audible to everyone? I hope. Fine. Okay. So the first thing, what is classification? So typically if you ask a school-going kid, a higher secondary school-going kid, periodic elements, chemical elements, they know even in the middle of the night if you wake them up, what element is, what atomic weight, what atomic number. Right? So atomic number and atomic weight giving is like characterizing every chemical element. No two chemical elements can have the same atomic weight and atomic number. Right? So that is what is called classification of periodic elements. And also I would like to say at some point that those days in 1700s, Kelvin had this brilliant thought. He thought that he can use this fluid model, fluid atom model, where he tried to say that you can see each of these chemical elements as if it is a vortex line entangled in the either medium. So he wanted to associate that you can put them as vortex line entangled in a either medium. Okay. So this led to the birth of one-to-one correspondence. They thought they can give a one-to-one correspondence with drawing these entangled kind of vortex lines, but of course either medium fizzled off, but the knot theorists or the mathematicians took over. Why not classify all of them? And this is the famous Rolfson table, where like chemical element, every such structure, this is like a non-trivial curve which is put in 3 dimension, and each one has some kind of a label. And that label tells you that this is different. This knot has 3 intersections, and this is different from this knot with 4 intersections, and so on.
This table goes on?
Huh? Goes on, yeah. They've been updating it, I think till 16 definitely is there, and they follow this universal nomenclature, like they find something non-trivial and they have to add with the appropriate subscript. So you see that the 5 crossing, there are 2 different diagrams for 5 crossings. So they are called 5 subscript 1, 5 subscript 2. This is the universal nomenclature, and we have to follow this. Whenever I say phi 2 naught, they will go to the Kizilweit or the Rolfson classification, and then they'll pick up. This is the diagram I'm referring to. Just like chemical elements. See, if I say everybody knows it's carbon.
What's the
2? 2, that's the way the notation is. 5 is for the number of crossings. Yeah. So similarly, if you go to 8 crossing, you have 1 kind, 2nd kind, 3rd kind, 4th kind, they're all different. Okay?
Why are the colors different?
No specific reason. Yeah. At least right now there is no specific reason. Only thing is that just like you have chemical elements with atomic number and atomic weight. Okay, I given like chemical element some letters, right, the number. But I should be able to give a quantifying statement like atomic weight and atomic weight. What is a nice quantifying statement? The nice quantifying statement is the crossing number or the intersection number. But definitely you see that 3 crossing, okay, there is only 1. 4 crossing, there is only 1. But when you go to 5 crossing, there are 2. So giving a crossing number is not going to say that this knot is different from the other. Right? You need another quantity which will lift that degeneracy. Right? You cannot work with the same crossing number as a nice quantity. Atomic number and atomic weight was beautiful. It is different for different elements, but that's not the case here. The crossing number is not the same for many examples.
Like very simple question.
Yeah.
These knots can be made in three-dimensional space.
Yes.
Basically, the dimension, do you think?
There are surface operators and
No, I mean, would this table of the kind of knot hold only for three dimensions?
this is only in 3 dimensions.
Does it go for four?
All of them
eight,
become a
17?
simple curve.
So
They all
for
become,
example, in four
like for
dimensions,
example, let's take 2 dimension. This one in 3 dimension is equivalent. If you are in 2 dimension, I don't have the extra direction to pull this out and make it like this.
Okay, fine. So in, for example, in four dimensions, it could have been that.
There is an extra dimension to make everything look like this first diagram. Is that okay?
So only surfaces will interact.
Yeah, if you want to make, if you want to go into 4 dimension, you should start looking at not lines, non-trivial curves you are looking at in 3 dimension, but you have to look at non-trivial surfaces in 4 dimension.
But they will intersect, not like we're linking, you would put 5 surfaces in 5. You can have lines and surfaces in 4.
Yeah,
That's not enough.
yeah. So you need to go to extra dimension. Okay, so this was just to motivate that on a plane everything is distinct, but if you go to 3 dimension, these two are equal. Okay. So crossing number, we say it is a very weak invariant. Okay, you can just use it to say that this knot is different from this knot, but you cannot say that this is different from this. Right? Okay, so then there is a set of rules which we can follow to say whether knot A is equivalent to a knot B. So that is called knot equivalence. So you have a set of moves which you can do in any region of a knot A and see whether you can get to knot B. This is nothing very different from topologically you can do pull and push. That's all I am saying, but it has been put as a prescribed set of systematic moves. So in any region of the knot, if you had something like this, you can undo it. This is called Reidmaster move 1. You can, if you have 2 consecutive ones going under the plane and over the plane, you can just slide it across. Similarly, this one is a rope going under the plane, you can just slide it across. So these are the 3 allowed moves which you can do in any region of a knot A, and the process of doing any number of times, any combination of that times, you can get knot B, then you say that B is equivalent to A. Okay? So then the work in 20s, I think by Alexander, started in writing an algebraic quantity. Like atomic number and atomic weight, you want to write an algebraic quantity which will say that the knot A invariant, whatever you write that quantity, should be different for knot B if they are inequivalent. If they are equivalent, they should share the same quantity. They may look inequivalent by adding these kinds of crossings, but you know that these two are equivalent. So if I write a quantity for this, if I write a quantity for this, because they are equivalent, those two quantities have to be same. So that is the driving force where a knot invariant, so to call it as a knot invariant, it has to satisfy equivalent knot should have the same quantity, inequivalent knot should have a different quantity. Okay? So this,
So, Rama,
yeah,
in terms of Chern-Simons theory,
yeah.
if I have some decent moves going as a knot, and then these moves, they mean some discrete symmetry.
No, this is like putting in a additional frame and then you have this framing corrections to be added to the, so you for every knot you This happens whenever you have an intersection point. When you do the propagator calculation in Chern-Simons, it will blow up at the intersection point. You do a regularization by slightly shifting it. And by regularization, by slightly shifting, you mean that you put a frame curve, another curve, which is slightly away from it and take the limit epsilon tending to 0 finally. That will give you the self-linking number or the crossing. Do you understand? No, I'm going to come to it. No, I'm going to come to it, but he went ahead. Anyway, so right now I'm just following whatever is known in the knot literature. So these are the recursion relation. This was in, in 1923, which is far after that. Only after 60 years, Jones came up to look at the variant. Okay, so here there are various other methods. In fact, Mahan has, he knows from various other approaches where there is a geometrical way you could try and give meaning to this Alexander polynomial for knot. For the present talk, let me confine myself to this recursive procedure where you concentrate on a particular intersection or particular crossing. That particular crossing you make it, this one is over, that you make it under that particular crossing. And so that particular crossing, following the orientation, if you put some arrows on the knot, you can accordingly make it into a no crossing. That particular other crossings you don't touch. In a knot you just concentrate on a particular crossing, and there is a relation. If you say that there is a quantity delta for that particular knot, that particular crossing being this way, replacing that crossing to be under crossing, it will become a new knot. There is a quantity for it, and so on. So you can write this recursion relation, and we can solve starting from 0 crossing knot, put the 0 crossing knot, which is the simplest unknot, this to be 1, and you can solve iteratively to find all the higher crossing knots gradually using this equation. Yeah.
How easy or difficult is it to write down recursion relations that we do by space? What sort of consistency conditions do these recursion relations?
Yeah. So the consistency condition is that the recursion relation takes care that this delta which I write for a knot will be same for equivalent knots.
So
that's incorporated, and we can see this from Chern-Simons theorem. Okay. So the construction is such that it has to be same for equivalent knots. Converse is not taken care of.
No, but there should be the local constraint also.
What constraint? I'm just going to put a constraint that or normalization that delta of this is 1.
So in other words, why can't I just write q square join
Here.
That should be consistent with the Ramadevi concept.
Yeah.
But this is arbitrary. But how is your
That
That's why these things are very difficult to get. Typically they come up from elsewhere.
But from Chern-Simons we will see that these coefficients are going to be like this. Okay. Okay, so the procedure is very straightforward. Only thing is here, if you take a knot and take the mirror image of the knot, okay, so this is what we call it as chiral knots. Right? You take a trefoil, and if I take the mirror image of it, all the over crossing will become an undercrossing. So this two knot and the mirror image, so if you take a knot, you do a mirror transformation, you get mirror literally, not mirror symmetry in the topological string context or string context. You just take the knot, suppose I had something like this and the mirror will go like this. Okay. So this will become an undercross. If you do this transformation, unfortunately the Alexander polynomial does not distinguish. Of course this diagram is equivalent, so it doesn't matter, but if you take any other knot, it is happening. So in some sense, Alexander polynomial is still weak in mutant. Okay. So if you go to a little variant,
So this is symmetric.
yeah, that's right. That's what is happening. So if you go to a little variant here, you can see that if you make this to this, Q to Q inverse symmetry is seen. The polynomials in general, like if you write the Jones polynomial, it will be in variable Q for a knot K. Okay. This in general may not be equal to with Q inverse. Okay. This possibility allows that the sum of the chiral knots can be distinguished by Jones. And this is another variation where you have two variables, and these two variables further enhance. So it's like this. You have a list of knots here. Suppose the Jones for all of them are same. If you do a two variable generalization, there will be some list which has different polynomial and another. It kind of lifts the degeneracy. It helps you to lift the degeneracy if you go from one variable to two variables. So this is a kind of, in fact I should say that there are 6 plus 2, 8 people. This PT independently wrote a paper, and this Homefly, Millet, Flo, Licorice, I forget, there is also Oceano. Who was Oceano? Huh? Oceano, yeah. Yeah. So this is Pretsky and Traxel. So these people have independently done, and this polynomial which is written is called the Homefly. Okay. So there is a kind of an improvement when you go from Alexander, then Jones came after 60 years. This definitely could distinguish many chiral knots, and then Homefly PT was doing a better job than the and it appears like if you go better and better, some knots are not distinguished, maybe the next one will distinguish. So you may end up getting a situation where if you have a list of inequivalent knots, that knot table, every one will have a different polynomial. That is the main target, which has still not been achieved. It's still an open problem. It's like two-dimensional surfaces when you have. If you have one Riemann surface, you will ask me what is the genus. Now what is the number of punctures. If I say what is the genus and number of punctures, Euler characteristic, you know that's a very good algebraic quantity to distinguish different Riemann surfaces. Such a quantity does not exist for three manifolds. That's still an open problem. Forget that, since knots are non-trivial objects in 3 dimension, we expect at least the polynomials for the list of inequivalent knots should be different. Unfortunately, none of these are able to achieve.
This is probably equivalent classification of knots and classification.
Yes, it can be made equivalent in some sense by doing a surgery. You can take a knot in a 3 manifold S3, you can do a surgery to go to a new 3 manifold, but then there is a class of knots whose surgery will give you the same 3 manifold. So we need to modulo that. That's called the Kirby moves. Okay. So the simplest problem is to first classify this. If we can achieve this, then we can attempt that problem. We know how to go from one to the other. Yeah, maybe you have something to add.
Yeah. So actually, yeah, the classification problem through polynomials is not solved.
Yeah.
But classification problem itself, I mean, as a formal classification problem, that can be solved.
For the 3 manifolds?
For 3 manifolds.
Huh.
That's via this Thurston geometrization.
It can be solved, but is
Yeah,
it been
can.
done?
It has been done.
Okay.
In fact, very relatively recently, I think somebody, I mean, it was sort of folklore, and
Okay.
they took over as a paper on our side,
I see.
maybe within the last year.
So classification of 3 manifolds has been achieved.
Yeah.
That follows from the comparison.
That follows from the geometrization. Another version.
Yeah, but from the invariants of knots.
From the invariants of knots.
Okay.
But that follows.
I think what is now again is something like, I think Barnatan, I think, was saying that there is some
Okay, so just for the benefit of completeness, I thought let me put the examples Hofflink and trefoil. So you concentrate on this particular crossing. You make this into an undercrossing. If you do that by readmaster move 2, it will become 2 loops. And if you make it into a no crossing, then it will have only this particular crossing. Okay. And you can write out what is the polynomial, taking the fact that this is unnought, and I'm going to normalize that to be 1. And then I'm also going to use the fact that this one is, this can also be derived, but right now I'm using this. In general, if you have this to the power of n, this will be n minus. Simple loops separated. Okay. So then once you have this answer, then you can go to the 3 crossing. So it is like this recursive method tells you that you should know the lower crossing invariance to go to the higher crossing. Otherwise you cannot directly determine this. So here again you concentrate on this crossing, you make it into an undercrossing, that will become unnought, and this will be a Hofflink. Substitute the Hofflink answer and you will get the answer. Okay. So this is what I was telling about this integer coefficients for the nodes, that every coefficient here is an integer. Okay, so this is also something which happens for any node. Okay.
What is this word? Trefoil.
So this is the, some of the nodes have been named, okay, the lower crossing ones. A simple circle is called unknot. And if you have 2 entangled circles, we call it Hofflink. And the 3-1 knot in that knot table is many times referred to as trefoil. Okay. And 4-1 is called figure 8. After that, we don't have really any name. What still? Why DNA? Maybe those knots which they use, but yeah. So this is the 3-1 knot in the knot.
So the integer coefficients are not necessarily positive. They can be negative.
Can be
They
negative.
are not counting. Or
They're not really, but then how do you do that counting to take care of it is what I will explain at some point. Yeah. Yeah, but the curious.
How does it solve?
This is for the link. Link, we are not talking about these integer issues. Yeah. Yeah. Half also there is a way of understanding, but let me not get into it now. Yeah.
That was my question. What were the half?
Yeah. So one is you can make a change of variable q to the half to q, and then you don't need to. This is what Witten says. But independently, you can also see from framing anomaly and so on. You will get q to the half, but you can replace it by some variable q to be t squared or something, so that everything. The only thing is that this q to the half has meaning when we do Chern-Simons. So that's why we're keeping this as q to the half. If you ask a knot theorist, he may just scale it to q cube or q power 4, or doesn't really. But this is the one which shows up in Chern-Simons. Okay. Is this, yeah. So before I get on to Chern-Simons theory, I thought at least diagrammatically I should show what is mutant knot pairs. So this is the famous 11 crossing, which is known for now so many decades, because one of the famous reason is that none of the polynomials for this knot or this knot, they were different. They both are inequivalent knots. Okay. What is mutation? Take this region.
So they're equivalent because you cannot do a series of line master moves to get from one to the other.
Yeah, the knot table, these two are, that 11 crossing, these two are inequivalent ones.
And the fact that you're only allowed these 3 moves,
Only,
where does that
yeah.
come from?
There is some rigorous way in which this is the one complete
Right.
set of allowed moves. You can't go do anything more or anything less.
I think the common word is isotop. Basically, you can move your knot. You are
Yeah.
free to move your knot.
No cutting and
in
snapping.
space
Without cutting.
without interfering.
Yeah.
And then randomized said that it can be reversed. I mean, it can be boiled down to zero.
This, if, like the way Louis Kaufman comes to any dinner table with complicated mess of thread connected, he says, Rama, can you just do something and get it like a knot? You know, it's sometimes it looks like a messy one, but to make it into a knot may require some work, and this set of moves can help.
My response is very easy.
Huh? Huh?
These moves are only when we project the knot to a two-dimensional plane. In 3 dimensions itself, if we try to distinguish
Yeah, you
knots,
can. Yeah, in 3
these moves
dimension,
are not really relevant.
it's not really relevant. You're projecting it onto a 2 dimension to do this, but the first readmaster move 1, you know, unknowingly or knowingly takes care that we are in 3 dimensions. Right? This one we did this. Yeah,
Three-dimensional equivalent is isotope.
yeah, isotope. Okay.
Polynomials would be this statement about the complement.
Oh, yeah, so that's a bit, that the complements of the knots are homomorphic by a homomorphism, by a orientation preserving homomorphism. That's a priori neutral. So isotope is that it definitely.
Yeah. Okay, so these 2 knots, why it is called as a mutant pair is that you take this region, this is sometimes in a mathematician way of saying, we call it as a 2 tangle. 2 of the, you know, the incoming curves and outgoing curves are there. Okay. So this 2 tangle, if I do a 180-degree rotation, okay, you can see that these 2 have got exchanged. Right? This has 3 crossings, this has 2 crossings. So it's a 180-degree exchange which I have done, or by which I have gone from this to this. So this 180-degree exchange is what is called as a mutation, and these 2 knots are different, and this is the mutant of this knot.
And then the upstairs should have changed too.
No, you keep the upstairs one region intact. You can do it in any region, this one, locally 180.
Very, very different.
Yeah. By doing the whole thing, it is the same knot, right? Like
That's right. I was always wondering 180 degree.
only on this pink shaded region, I am allowed to do 180-degree rotation and fit it back. You no. This mutant operation is seen as an identity operation for well-known polynomials. If suppose I do the recursive method and work out the well-known polynomials for this case, it's same as this one, but these 2 are inequivalent.
Is there a no-go theorem from Chern-Simons?
Hmm?
Is there a no-go theorem from Chern-Simons?
We do have it for symmetric representation, then we find that they can be distinguished by mixture. But of course, Morton in, I forget the date, it's probably in 2000, he has a way of putting it in a computer and doing quantum groups with specific SU4 with representation which is like the octet diagram in our, and he did show that these 2 are distinguished by only finding the difference. But now we have a nice methodology of working out the invariant and showing that these 2 are different from Chern-Simons. Okay. So in that sense, Chern-Simons seems to be getting better, powerful than the well-known polynomials, but we still are, I can't claim it is it's an attempt towards classification. For example, these 2 knots are distinguished.
So formally, this is done in what, in the language
I'll go through the proof. Yeah. Okay. So that is so far what is the general availability and what is the open problem. Open problem is at least can you find a way of distinguishing the mutant pair. Okay. So this just to give you a Chern-Simons theory is a three-dimensional, you can write an action in 3 dimension with some coupling constant. I have not really written down this, but so in typically any quantum field theory you will have an action. So this action will be on a 3 manifold, which we will take it to be S3. Okay. And you have ADA plus 2/3 AQ. So this is the Chern-Simons action. The small k is the coupling constant, and you can put in gauge invariance and a large gauge transformation. You can show that k has to be an integer. So in such a quantum field theory, you can work out expectation values of observables, and those observables which you would like to choose are the Wilson loop operators.
So the connection A is independent of the connection.
Which one?
So
You're going to integrate over all the,
do you take the connection? Or
A is, yeah, so like
It's a functional integral.
functional integral. So when I want to do the expectation value of any operator, what I will do is I have to integrate over the space of all gauge fields modulo gauge transformation. This will be the space of flat connection, because the solution to this action will be f equal to 0. So that will give you the space of A, which is the space of flat connections. Okay. You have to integrate that with e to the is O operator in the Euclidean language, and then you will have, this is the normalization. You can also call it as a partition function. In our way of looking at it, we also say that this has information about the 3 manifold. If I take it to be S cube, this will be the partition function for S3.
why do you want to integrate onto a flattened theorem?
That's the solution, no?
You don't integrate over solutions, right? Quantum field theory you integrate over
Yeah.
all things.
So this is integrate over all gauge fields modulo gauge transformation. Yeah. So I'm just trying to say that it's going to pick up the solutions. Okay. So this will pick up everything. Okay. Formally, yes. Yeah.
You know is what SU2 or SUN?
Yeah. Good. So here, if I take the gauge field, I should write this to be valued in some algebra valued. So you can take it to be SU2. So the list of groups we can take are SU2. You can have SUN, SON, and so on. Any compact groups list. Okay. So this invariant is going to be, as I pointed it out, depends on the gauge group. So this observable, which I wrote as O operator, any observable, that should be the Wilson loop operator. And Wilson loop operator will carry, suppose I am doing SU2, it will carry some representation, spin half or spin n by 2, and G is the group which will be SU2. Okay.
So there should be also a version of this where you don't have a knot, right? And just for 3 manifolds itself.
Yeah, so that's the denominator. Yeah, that will give you the partition function or the 3 manifold integral. Yeah. So the denominator which I have written can also be treated like a 3 manifold invariant, which is in the physicist language we call it as the partition function. This one. This is going to be in terms of the modular transformation matrix. This turns out to be S00 or something, but maybe the expansion of it, the leading term up to order k squared or something, we can extract, and that will be the cascade. Okay.
Laurent, so just to go back to this question, so you are not doing
So whatever I'm going to write as an invariant, it should be a function of coupling constant, it should be the rank of the group, it should also be dependent on the group also, right? And the knot which I am going to consider, or the Wilson loop which I am going to
And
consider.
the representation concept.
Yes, yes, that also I should put it. Yeah. So the representation, let me put it. Yeah.
So it doesn't depend on the size of the distribution.
No, that is why the Chern-Simons theory is independent of size and shape. Yeah. Okay. So this I am formally writing it as P tilde. The reason why I am putting it is that there will be some normalization with the well-known not polynomial, overall normalization. So this is given by the expectation value of the Wilson loop operator, where the Wilson loop carries a representation R of some compact gauge group, and this evaluation, whatever I get, if I want to call it to be some polynomial invariant, it should be a polynomial. I have to figure out how the Q in that recursion relation was written in terms of K, capital N, the coupling constant and capital. You need to figure that out. Okay? Yeah.
G of x is some function of k, right? And that's all there is.
In some sense, the denominator, yes, the partition function is some function of K. K and yeah, it is not a function of representation,
Yeah,
because you have to integrate over all. Right? There are no knots.
Yeah.
Another way of saying is that in the surgery language, we take some knot and we do summation over all representation and remove the information about the knot. In the process, the manifold changes from S3 to something else. Okay, so we suppose I take this in S3. Okay, so like a doctor, if I thicken this and do some kind of a surgery on it, in the process, I will end up getting S2 cross. With identifying this. So this is sigma g equal to 0 and this is R, so let me call it as S1 by identifying this with this. So such manifolds you can get, but algebraically when I write, I sum up over all representations of the knot, all the allowed representation, then I remove the representation information and I get only the partition. Okay? Okay, so K is the knot and R is the representation of the gauge group. Jones polynomial, which I listed in the earlier slide, that can be shown to be in the polynomial variable. K is this coupling constant, and you have this, and for the spin half representation. Spin half representation, if I put on the knot and if I am looking at the gauge group SU2, you can actually, this is the famous work of Witten, where he got the same recursion relation by looking at the, the braiding, which we call it as a monodromy matrices. If you try to write the characteristic equation of the monodromy matrix, you will have the characteristic equation to be like alpha times monodromy matrix beta times B plus gamma equal to 0. Okay. Another way of looking at it is that you take a simple piece like this, and if you do B squared on it, it will give you two crossings, and you can remove this. That will be alpha times this plus beta times 1B you have to do. So you will do one of them, and then gamma times equal to 0, and then you cap it with and how will you fix these coefficients alpha, beta, gamma? If you know this monodromy matrix, diagonalizing it will give you the product of eigenvalues to be gamma by alpha, sum of eigenvalues to be beta, and so on. So he actually showed this recursion relation can be reproduced, the Jones polynomial recursion relation.
Then this is too fast. What do you
Yeah. So alpha, beta, gamma are some coefficients, right?
What is this B?
Okay.
Yeah.
So this B is some operator. I'm saying that the exchange which we do in Chern-Simons monodromy matrices, okay, those monodromy matrices can be shown to satisfy this characteristic equation. This can be shown.
Monotony as I am taking what around what?
Yeah. Half twist.
Can you slice it, look at the spatial slice?
Half twist.
This will then you, what is the W model?
Yeah. So if
Then you are looking at the, what happens if you put the
Monotony of that WB.
yes. So, yeah.
So do you think some this is going to be what a braid on these strands and this
Yes.
is a standard braiding operation?
Yes. Yes. It's the same. There is a one-to-one correspondence between that and the monodromy matrices in the Verzimino-Witten conformation. Okay. So I'm just independently saying that there is a characteristic equation satisfied by that. If you plug in this characteristic equation as an operator equation operating on some state and take the state to be like this, you will get a recursion relation which is exactly similar to what you got for the Jones polynomial. With the right coefficients, because you have to substitute the product of eigenvalues here, you have to substitute, product of eigenvalues here and sum of eigenvalues here, and you will end up getting the same recursion. This was the work of Witten in 89, where he reproduced Jones polynomial by systematically trying to say that to solve Chern-Simons you can go and do the, I'll go through the steps. What are the relevant indications? Okay? Okay, so right now you take it as if you put a spin half representation on the Wilson loop, and if you take the group to be SU2, then up to overall unknot normalization, you will get the polynomial in variable q of Jones. The q is related to the coupling constant, and I've got an answer. I am not specifically writing it in terms of arbitrary n by 2, so that is why I don't have. Okay, and I'm also specifically looking at the rank 2 SU2 group, rank 1. So in the same method of doing it, this methodology will extend to SUN also, and you can put a fundamental representation of SUN, and you will again get a polynomial. Now the polynomial will depend on k, it will depend on n as well, and the two variables can be related. So in fact you can show that there will be two variables. So the q to the n turns out to be a and q is k plus the quadratic Casimir in the adjoint representation, and CV will be 2 for SU2 and n for SUN. And so on. So if you go to SON, and if you take the vector representation, you will get a polynomial, and that polynomial will turn out to be what Kaufman had proposed. So in some sense, Chern-Simons seems to give a way of writing expectation values of spin half or fundamental representation of SUN to actually account for my invariance. In the same language, if you want to extrapolate what is Alexander, then you may have to do what? N equal to 0 limit you have to do. That turns out to be very nice. Okay. So anyway, so why these polynomials cannot distinguish mutant pairs is the question which, and what you see from the slide is that
It's not U1.
U1 only gives us linking number and self-linking number. We can do U1 Chern-Simons. Yeah. that's what we're saying, no? Chern-Simons allows for a huge pool of invariants. That's exactly what I've said. We have more generalized invariants for arbitrary R and arbitrary G. So this is the way all physicists think, right? We all want to get more information from the formal definition. So once you do this for arbitrary R and G, at least one R and one group will be able to distinguish mutant pairs. Right? Then I'm happy, at least I'm able to distinguish an open problem of Kinoshita and Conway which has not been distinguished. Yeah.
So what's the problem? It's difficult to calculate justification very well.
No, it's not difficult. That also Witten has put it very nicely. We just follow that methodology. In fact, we even don't go through this recursion method. Recursion method allows you to know the invariant for lower crossings to go to higher crossings. Right? It's called the scheme method. So we would like to directly evaluate. We can do this. We have done it. So this is the theme of this talk. So, thank you. So the not invariants you can evaluate using the following inputs. Okay. So this has been elaborated in Witten's work. One is that I will show you with diagrams on an example, which is the 3-1 knot, which is called trefoil. So there is a way in which you can relate functional integrals of Chern-Simons on any 3-ball with a boundary to a Vesimino conformal field theory on a boundary. See, those days also like ADS-CFT, why ADS-CFT or even those days? Gauss's law is based on, you do a volume integral and all the informations are there in the E dot ds takes care of del dot E times dV. So this is a kind of a volume to a surface, and this volume will have a boundary, and on the boundary you will have a conformal field. Okay. So this is the affine Lie algebra restricted by this level K is what we say. So it's like a central extension which comes up in the conventional Lie algebra. You have a central extension. Yeah, the current algebra, if you take the
same group as in
yeah, same group. So you will have the, see in SU2 you just have J plus J minus to be twice Jz or something, right? So you will have one more here which is Jn subscript with 0, Jm or so this is the other index which I should put it as A, B and C. So you will have an epsilon ABC, Jn plus M, C plus K times something. You will have a central extension of delta n plus m comma 0. Yeah, so this is the current algebra, whereas Laurent will have generators which are Ln and Ln. This will have the central charge as the extension, right? You will have Ln plus m. Yeah, so you will have n cube minus n delta n plus n comma 0, L0 or L0. Yeah, times the C. So you will have a central extension there. This is purely for your conformal transformation. This will come from the internal symmetry of the group, which is with a central extension. This is sometimes we call it as an affine Lie algebra. Yeah. The only thing what happens in this group is that whenever you take two spin half particles, when you compose two spin half particles, we blindly write it as spin 1 and if you take spin half particles, we compose them, we would have written this as spin 1 plus spin 0, right? This is what we would have written. But here in this case, you should write it as summation over or direct sum of S, which is J1 minus J2 to K minus J1 plus J2 minimum. to be the S. There is a slight modification. If k is very large, you don't need to really worry about it. But if k is finite, then there will be a cutoff put in by that. Okay, there is slight modification because of the extension which we
J1 cross J.
in case of J1 cross J2. Yeah. Okay.
So this relation comes from the current algebra.
This is coming from the current algebra when you compose two primary fields. So technically I should write this to be a primary field J1 with conformal weight head J1, which is given by Cj by k plus 2 something like this. Okay. So composing
Says that it should be in equilibrium. Is there an analogous statement one can make from the Chern-Simons? If we take two Wilson lines in J1 and J2, is there something that tells us that on the right hand side of it, or in the answer
so
for
the
this,
thing is the
we see only this restricted.
yeah, so this comes from only saying that the finite dimensional vector space is given by the space of conformal blocks here, right? Like,
but
so there is a one-to-one way in which it has been rigorously said, but I don't understand by explicitly looking at Wilson lines in Chern-Simons how to do this.
So
Yeah.
is there an intrinsic three-dimensional derivation?
No, I don't think so. At least I'm not aware of it. Yes. That's the statement of this first line, that you will only work with those integrable forms. Okay. And other thing is, other input is that whatever diagram I get, first I redraw them this way so that I can use this monodromy matrices in the Vesumino conformal field theory nicely. If I don't redraw them, then I find it very difficult to do. So this is all for calculational proofs. Okay. So unknot is just a two-strand which is just capped. You can see here it is 3 strands and the 3 crossings between 2 strands, and then I put a capping. This is called plaiting. Quasi-plait is when you follow closure here. Closure is the, so you have an arbitrary braid word here, okay, and closure means that you identify these points with these points, which means, and you go and connect them. Okay. So this is what is closure. So you can see that there is a half-baked closure here and a plaiting here. So these are called quasi-plait braids. Okay. So there are some diagrams which I have drawn it as purely plaiting. Plaiting means you just duplicate the strands.
So Rama, just one.
Yeah.
Your model here is a solid ball, and the little bits on the surface of that machine.
Yeah, I'm going to come to it. I'm going to explain it for an example. Right now I'm only explaining that every knot can be drawn this way. I'm coming to that. Then that will answer you the question, point 1. So if you take a knot, which is the 3-1, which I call it as trefoil in S3, okay, the way it goes about is that this invariant should be a number. You can equivalently work it out by gluing 2 3 balls with oppositely oriented S2 boundaries, and the S2 boundaries have 4 punctures, 1, 2, 3, 4, okay. So you're going to look at the Vesumino conformal field theory where each of these punctures has primary fields of the SU2K if I'm looking at SU2 group, and I'm going to do the usual fusion of different matrices which I did. Okay. And what you will get is that you will get a state in that conformal field theory, and this is oppositely oriented, so I will take it in the dual space. And once I know these two answers, the inner product should give me the expectation value of the Wilson loop in S3. So this is the point 1 which I pictorially elaborated. So Chern-Simons functional integral on a 3 ball with S2 boundary is given by a 4 punctured. So you will have a correlator 4 point function, or you can call it as the 4 point conformal block. Yeah.
The capping on the bottom is something that you are keeping fixed. Is that right?
You can keep it fixed, but you can also put in the braid word. Suppose out of this 3 you could have put 2 here and 1 here also. You could have done.
I think what I'm worried about.
Mm.
For example, you have your 3 ball on the top.
Hmm.
So you can, if you are allowed to move the boundary 2 sphere,
Hmm.
then you can keep unknotting it inside. So there is some, you are recording the information that
No,
that
given,
it is braided inside.
I agree. So if I am going to look at this diagram, I am equivalently going to represent by this diagram, or I can have any series of diagram, but this goes to this diagram only. So that information is going to be fixed. Like your argument is that here I should put all the crossings and no crossings here. That is not true. I could have put 2 crossings here, 1 crossing here, or vice versa, whichever I want.
No, I guess what I'm trying to answer is essentially what it means is that on the boundary sphere you have these 4 points.
Yeah.
If you look at how, so you're starting with some stand, and basically whether the loop, whether the string inside is moving around this or not. By
Okay.
moving in just the sphere,
Yeah.
you can undo all that winding.
I see, I see.
So somehow
Okay.
that 3-dimensional information,
Yeah.
you need to record it in terms of, say, a diffeomorphism,
Yeah.
those marked points.
Yeah, another way in which I am looking at it is that at the 2D boundary, I will do 3 exchanges.
Yes, basically you are doing some.
3 exchanges.
Yeah,
That's
the-
all I am
the
doing
braid
at the
operator.
2D boundary.
That's right.
But if I am doing it as if it is a 3D, then 2 exchanges can be equivalent to no exchange, right? But that is not true if I am confining to the 2D boundary. So that is also an information, like this 3 braids that it corresponds to 3 exchanges is confined to the S2 boundary,
Correct.
which is going to be
So
non-trivial.
you are looking at a 4-pointed sphere, and then you are
Yes.
extending 2 points.
Yes, only the 2 points 3 times, okay?
We are essentially looking at this interface of Chern-Simons series with punctured spaces like 4 points, and it's a finite dimensional space.
Yes,
Now you take this around that, and that induces an operation on the
Yes.
reverse space, and you are recording those operations. as
yes,
well.
that's exactly what we are doing, yeah. Okay? So the not invariant which you write, this is the space of correlation functions in the 2D field theory, which can also be pictorially denoted by the conformal blocks. We call it as S channel, T channel. You can, so 1, 2, 3, 4, 4 punctures. You can put 1, 2, 3, 4, which is 4 punctures. So at least for the 4 punctures, these are the 2 kinds of, if this is associated with the 4-point function, I can also call this as a conformal block, which are of 2 types.
So the dimension of that space would be the
Yeah.
number of representations.
Yeah.
that
So
can
if
close
suppose
to the-
this representation is J1 and this is J2, whatever is this S, the number will give you the dimension of that. Okay? Okay. So formally we can write the inner product of the 2, which will give you the not invariant for 3-1, which we call it as a trefoil T, and that can also be formally as we discussed now. These 2 punctures can be exchanged thrice by the half twist monodromy matrix. Okay. So still we have not written the polynomial, and I am doing it directly. I am not going through recursive method. To do that, you have to only go to the eigenbasis of the B operator. Okay. And this is also known to us that as okay. So these are the 2 allowed eigenbases of the braiding operator, and these 2 are related by some kind of a duality matrix, because both are equivalent bases and they should be unitarily related. Okay. I'll explain a little bit on this, that T and S, this is like your T channel and an S channel. where you can relate this, and you also keep track of what are the representations or the primary fields which are put on the functions. Okay, and this is the, so for knots, two of the representations will be R, because for knot it is a single representation which is going around, right? If you have a link, you can have more than two representation. So even though I have written R1, R2, all the strands carry the same representation, and whatever goes out of the boundary will come back. So there will be equal number of representations which are entering S2 or leaving S2. If suppose two of them are going out, these two better come back. Okay. So in our Chern-Simons language, if I put representation R for going out of the boundary, I better put R bar if I am doing SUN. For SU2 it doesn't really matter. Okay. So these are things which we need to take care. Two of the RIs will be R and the other two will be conjugate depending on the orientation. And then we have this formal, formally we can write psi 0 in terms of those diagrams, and we should fix this coefficient, and that is fixed by an unknot normalization. We make sure that we write the unknot normalization for any representation in terms of dimension of a representation. This is slightly a variant of the dimension of representation, because if you take spin half, you would have written in SU2, you would have said the dimension of a representation is 2. But now it will become a Q dimension. It's like classical mechanics to quantum mechanics, where if you take H cross tends to 0, you have to get back your classical mechanics, right? Like this is the way you look at classical mechanics to quantum mechanics. So in the same way, the Q number can be written as Q to the half minus Q to the minus half, oh sorry, this is Q to the whatever is this number. Suppose there is a Q number n, it will be this by Q to the half minus Q to the minus half. The only thing what you have to remember is that Q, suppose I want to connect like what we do in classical to quantum by writing it as e to the IH cross. If you take H cross tending to 0, it will give you the ordinary number n. If you don't put H cross to 0, then this gives you the Q number. So this is what is called as a quantum deformation, and it's nicer to see half cross half, which is 1 plus 0, you can write it in dimension, which is 2 cross 2 is 3 plus 1, and the Q numbers also satisfied. For students, you can check out these exercises, that for every number there is a Q. Yeah. Psi 0 is the diagram which I had in the lower. Yeah, kind of, yeah. 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 So this H cross should not be treated like Planck constant. I'm just making an analogy. So I'm just saying, in fact, there's an ocean of work on quantum groups, right? Quantum Q calculus, Q integration, Q differentiation, everything is systematically done. Yeah.
There's a large K.
Yeah.
Is the classical.
That's right. I agree with you. Yeah. That's right. Yeah.
Yeah, I was.
Yeah. So H cross, if I replace it as proportional to 1 over K, K very large is like the weak coupling limit, which is like a semi-classical or classical. Okay. So this is the 0, psi 0, which someone was asking. So this diagram, or you can take this to be the psi 0 without the crossings. Okay. So that you can rewrite it in terms of basis. First, to see the polynomial form, you have to write it in basis, and these coefficients can be fixed by some unknot normalization. I'm only saying that the consistency with the OPEs of primary fields and so on forces us to choose this to be quantum dimension of a representation, and I was explaining what is quantum dimension of a representation. For spin half, you would have written the dimension of a representation as 2, but you have to replace it by Q number 2. What is Q number is, this is what I was saying, and if you take H cross to 0 or Q tends to 1, you will get back your ordinary dimension. I just gave you as a working knowledge. Is that clear? Okay, so then the invariant is just 3 times operating, and you will have an eigenvalue to that basis, and that eigenvalue will depend on the conformal block which we have with representation T or S, which you have to take. Okay.
Two dimensions, is it some kind of character? I mean, in the sense that.
Yeah, so this Q dimension, the way I perceive is that the quantum group people have done the SU2 algebra, which is the quantum algebra. When they do it, they find the finite dimensional representations are obtained when Q is a root of unity, and there is a one-to-one correspondence between the primary fields in your Vesuvino model and the representations which you find in the quantum groups. And I think the Q dimension is coming because of this.
Even in current algebra, if we calculate the character on the torus corresponding to that particular primary, and then take the torus parameter to the Q equal to 2 pi I tau, tau to I infinity, then we'll get this number which is called the quantum number.
Yeah, that's true.
Which is also the ratio of S, the modular S matrix with 0 and that particular primary divided by S0.
Yeah, yeah, I agree. No, but he is asking a little more question that why Q dimension. I am just trying to see that there is a kind of isomorphism between the finite dimension representation of quantum groups and the
but the general
primary
understanding
field.
of a character is if we evaluate
Sure.
the character at
I
identity,
yeah.
we'll get dimension of that representation.
I agree with you.
This
Yeah.
is the closest statement.
Okay, so we put in this eigenvalues. This is from the conformal field theory, and there is a slight frame correction to take care that the invariant which I evaluate for this is same as the invariant which I evaluate for this. So there is a frame correction, and once I put in this, what I get is that for spin half representation, S will be 0 or 1. Let's take K to be large, and you can check what this polynomial turns out by substituting it here. Okay. So I will leave this as a exercise for, if you remember, we had a Q plus Q squared minus Q cube from the recursive method for the 3-1 minus Q cube. I think this is from my memory, but you can write this evaluation with S is 0 and 1, dimension Q of S, and then you can write the lambda S plus the whole cube. Okay. So you can substitute this, and then you have to also divide it by the unnought invariant, and the unnought invariant is for the spin half will be dimension 2. So do this. Quadratic Casimir's, all of you know, for spin half is, for any representation is j into j plus 1, right? Know this. So you can write that out and write the polynomial and check that you get the, substituting it here and dividing it by q number 2, you get back this answer. So this is just to give you a working knowledge of how an example which is trivially a trefoil, which is a non-trivial example, can be worked out. So one more non-trivial example is the next 4 crossing one, which is sometimes called as figure 8. Again the same procedure, no change. But what is the change here? Can somebody tell me? You have braiding in the middle too, or exchange between 2 punctures in the middle. As after that you have exchange between the sides. Right? Is that right? So this is what is involves, and also if you put the orientation, you will see it is anti-parallel. So it will be R and R bar and R and R bar. Okay. So it involves anti-parallel braiding, and duality matrix has to be used, because when you want to do it on the side strand, the basis will be, you have 2 bases. You have this basis which is useful if I have to do the exchange between the side strands. So let me call it as B1 if I do it on this. This will be an eigenstate. Okay. If I want to do B2, the convenient basis is this. Why? Because I want to do the exchange between second puncture and the third puncture, and this is the right basis, eigenvalue basis for B2, which will give you lambda 2. And we also know these two are equivalent bases and they are related by a duality matrix. Yeah.
I think I missed your comment, but is it the case that all knots can be made with these 4 strands?
No, no, I'm going to come to it. This is what I also thought, but it is not. Yeah. The Russians came and pulled out a Russian paper and showed that not all knots can be drawn this. Yeah. But at least many knots with lower crossings, yes, the statement is fine. Okay, so using this procedure, mu s, mu t, then there is a duality matrix. There are 2 crossings in the middle strands, which is antiparallel. Antiparallel, I am putting it with a negative sign. And again, you have antiparallel, but it is the inverse of the crossing which happened here. So if you put in everything, you get the invariant. Yeah.
From changing the lunch time, is that right? For remaining one hour. I thought it was no, today the lunch time is still
Can you check? We don't want to miss lunch.
no, it is 1:30. Normally, our PhD talks go on till 1:30 because of the lunch deadline. Otherwise,
Yeah,
you don't
sure.
get anything. But if it is advanced by a couple of half an hour.
Anyway, I can put a break at some point, and if required, I'm anyway in Bombay, so I can come sometime and continue and tell. Okay. Shall I continue or should we wait for? Yeah. So this is the way we write the invariant, and you can substitute the quantum dimension and all. I explained how to write the quantum dimension. At least for SU2, the only thing which is missing is this, right? We can take equivalent knots and look at the properties of this duality matrix. Interestingly, the properties are, so the properties turns out to be exactly like the Raka coefficients of the Wigner 60. So that is where we go and look at this quantum. Just like we have quantum dimension, there are also quantum CGs, there are quantum 6Js, quantum 9Js, there is an ocean of literature on it. So we don't need to work it out. At least for SU2 case, they are available. So we can use them, the quantum 6J, and we can substitute and get the polynomial. So using this procedure for any knot which is drawn as quasi-plait of braids, at least we know how to work out the polynomial invariant. Okay. So I hope I have convinced you. The next question what Abhijit was asking is that if you go to many other nodes, typically what we could do is that you could try to put 4 punctured S2 boundaries, many such S2 boundaries. Okay. So for example, this diagram which I have drawn here is, it cannot be done just as a quasi-plait of 4-strand braid, but you see this junction is like a 3-point vertex, 3-point vertex. Okay. So if you try to shrink all the 4 strands into 1 strand, you see as if it is like a 3-point vertex. Okay. Here you can treat it like it's like a k-point vertex. Each of these are sometimes called as fingers, but inside the fingers you can have crossings between middle strands, side strands, all possible combinations, but at the end all of them are connected this way. It goes this way, it goes, you see that. Okay, so this is a 3 fingers, huh?
Are all knots of the class?
No. So the knots which are on this class are called arborescent knots, Okay, this terminology, I don't know whether you knew about it already. I didn't know about it, and we got to know from the Russians that they are called arborescent knots, and not all knots can be drawn this way. There are 817 crossing. It's like a tree. In fact, we wrote the other paper as if it's looking like a Feynman diagram. I'll come to it. But the knots which can be drawn this way are called arborescent. There are knots like 817 which cannot be drawn this way. Okay. So interestingly, you will see that I have given you a building block where how to do the braiding operator, how to go from side strands to middle strands, but I should also give how the states for a 3-point vertex, 4-point vertex, multi-point vertex can be required to evaluate the knot invariance for these diagrams.
Is there a nice braid representation?
Yeah.
Numerical braid representation that is available for
Yeah. That is available, I think, up to 16 or even more.
What?
The braid representation.
So that works for all.
Yeah, but I don't know the Raka matrices. I don't know how to evaluate the unity. Yeah.
The braid representation
Yeah.
that's available which
Yes.
works for all.
Yes. Closure of braids. Closure of braids.
But
I'll
is
explain.
there a
Yeah, it's there.
number?
No, there is no fixed.
No.
It just increases, right?
It keeps increasing. Oh, you are asking with 4 strands? No.
Not four, but some.
No. It keeps increasing.
If I have this, Y-like thing, it's
Huh.
like a Banks diagram string theory.
Yes.
So my immediate apprehension would be that there is no second pointer restriction at all. I mean, Western after all is the second, the first pointer. It would look like there are two, whatever.
Yeah.
One, so there's one string, there's another string, there's a tensor product of two Western models.
No. We don't. No. This is the invariant for that whole diagram which I have. The invariant for this will give you an
So
arborescent
you
knot.
just cut it any which way and somehow.
Yeah. Like for example, if you had this mess, this diagram mess, I can first redraw it this way. Once I redraw it this way, I know how to, like this one is the chiral knot. In fact, we took this specifically because the chiral knot, the chirality has not been detected by well-known polynomials. And you can redraw this diagram as if you have a boundary with 3 S2 boundaries, then glue it with this conventional one.
That's what I mean. So this is like string theory.
It is like string theory, string field theory, but I am saying
No,
this.
what I mean is that you need some object
Huh.
which has three boundaries.
Yes.
So it's a
Yes.
tensor product of
Yes.
three
States.
tensor spaces.
Yes,
Okay.
the states will be like the product of this. I agree. So as you already said this, so this is the 2 boundary with a braid word. You can have a single boundary. One is the cap state or the closure state. You can have 3 boundaries like this. You can have R such boundaries. You need to write what is the state for it, and it's a neat way in which you can write the neat state. Okay. So this also has been fixed by equivalence of knots, and it is working. Okay. So for a single boundary, we have already seen that it is a root of dimension q of t, which is correct with a single. So for every boundary, you will have a 4-point conformal block products. Okay. So using this,
Is it a collection of states or is it a single state?
the T will be the tensor product of 2 of these representations. It should be the intersection of all the
So earlier we just had a sum over one
T.
T.
Yeah, it's the same thing here also, but this T will be in the universal subset of. So if you have,
Oh, if we take tensor product of 3 of those.
so suppose your R3 cross R3 will give you a list, R2 cross R2 will give you a list, then you have to have the common intersection.
So
It's a single T.
it's the common intersection of R of those.
There are R's which are there. Okay. So once we have this, suppose you have a diagram like this, you can equivalently draw it this way. Where I know how to write the state for this, I know how to write the state for this, I know how to write the state for this, then I can write the state. by taking inner products of the appropriate boundaries. So it's very simple. It goes like, if you want to do this, again this is 2m crossing, 2m plus 1, it is odd number of crossings. Instead of this 2m, you will have odd number of crossing with the orientations appropriately changed. So similarly, if you have this diagram, you can redraw this as if it is this piece, and then you add 2 more crossings. So this is equivalent to this, but I know how to work out this piece from here, so I can use that and do this. So similarly, odd number of crossing. If you have something going as a loop like this, you can redraw it this way. So then here, if you look at this boundary, it is like B2 and B1 and B1. No, B1, B2, B1 and B2. So I can do this systematically and get all my answers rewritten in terms of grading eigenvalues and the duality matrix. Okay. So someone was asking, so tree kind of arborescent and so on. So typically this one is drawn like with some, here one crossing, middle one crossing, just to take care of. You can compactly write it by putting some integers. So sometimes we also follow a notation like, if it is anti-parallel, we'll follow integer with a bar. If it is right-handed or left-handed, we'll put a minus sign or a plus sign and so on. So there is a nice way in which we could write and draw it like a Feynman diagram. Arborescence can be drawn like tree with this 3-point vertex, 4-point vertex and so on. And given this, the end it is all fingers. So given this, you will write an invariant. So the beautiful question which this Russian team was asking us is that, can you write one universal formula? Take one complicated, just like you are asking for an arbitrary, all the braids can it fit into some, so at least up to 10 crossings. Can we write one universal tree diagram and write a invariant? If I put those parameters appropriately, I will get 3, 1, 4, 1, 5, 1, 5, 2. So this I think we managed to do almost for all the 10 crossing, but still the list which is missed out is still, I can call it as finite number, because I think how many crossings, how many knots are there in 10? 250. So but still we managed to do this much, which we call it as a family unit. Yeah.
Is the set of knots countable? It will be different by different.
For higher the number of crossings.
Build a knot out of finitely many straight lines, right? Because we have chain knots. So you fix a number in, then you do the various angles. For each fixed cell, there will be finitely many combinations.
Okay, so the interesting part in arborescent knot is that it will always involve states in the 4 punctured boundary, and I can work with only the 4-point conformal blocks as states. If you did not draw it like this with some n punctured boundary, then I will have other types of matrices, duality matrices, which is very different, and that you need for non-arborescent knots, because non-arborescent knots cannot be drawn. Okay. So just to summarize at this point, so you have duality matrices, and I know those values by looking at this quantum vector Sig symbol. This is given by Kirillov-Rishtikin. I can pull out those values, and I can write the colored zones. It's called, technically called, zones is for spin half. Anything beyond spin half is called colored zones, and n is the number of boxes, which means it's spin n by 2. Okay. And what is interesting is that with Satoshi and Zodin, we managed to get a Kirillov-Rishtikin type of SUN. Okay. But if you know SU2, all the representations are only symmetric representations, right? SU2 representations are only symmetric representations. So for all the symmetric representations, we could get from our evaluation of twist knot results a closed form expression for the duality matrix, which is the Raka coefficients or Wigner 6J for SUN. So this was considered to be one of the important results, because now all arborescent knot invariants at least for symmetric colors, can be worked out because we have the data. Earlier it was not available. Now it is available. So all arborescent knots, we can work out the invariant in polynomial form. By invariant working out, I mean you write all your invariants in braiding eigenvalues and duality matrices, but now you know the duality matrices in terms of variables A and Q, so I can write this as a two variable polynomial, which was not possible earlier. Okay, so this was one of the results. And getting back to mutants, formally if you take a region and if you do a rotation about x-axis, 180-degree rotation, you can get this, and you can do the my rotation about y-axis, and you can get this. You can also do a rotation about z-axis, but that can be seen as a linear mx, my will be.
Necessarily conducting on an arborescent knot, or
Not necessary, I think, no. It could be done, but at least we wanted to.
You need a satellite knot. That's
That's all,
probably
yeah.
enough.
But Kinoshita and Conway can be drawn as it's an arborescent knot, and we wanted to check the invariant whether these two are different. Not all mutants. This operation does not say that the knot has to be. You just take a two tangle in an arbitrary knot, so you don't really worry about whether it is arborescent or not. For arborescent, we have a methodology of working it out, and that is the only reason why we were. Okay, so this is one thing which we can actually prove, and I will show that step. So mutation is seen as an identity operation. This we will show that for any symmetric colors. So that is why SU2 or SU1 fundamental cannot distinguish. Okay, so it is seen as this mutation operation is seen as an identity operation. Whereas if you go beyond symmetric, if you want to go beyond symmetric representation, you have to go to SUN and look at mixed representation. That is the only way. Okay. So what has happened is that in 2014, by using identities and pentagon identity and so on, Zhu and Jokers obtained the duality matrix where our representation is taken to be 2, 1 in the Young diagram. We have all our invariants for arborescent knots involving duality matrix, and if I know the duality matrix, I can substitute. That is the status in which we are. Okay. So what we did is we used his answer, and we could work out for the mutant. So they are indeed distinct. Okay. So the 2 uncolored, if you put it on the 2 mutant pair, we can show that the polynomials are actually different. So this is going to, after a lot of, the style of our writing was not in shape with Journal of Noetherian Ramification. Recently, just before coming here, 2-3 days ago, the paper got accepted. It's a 2-year-old paper. So went on back and forth because they were, of course, it polished our way of presenting it, which I am going to present it here. But it's interesting to see. One of the crucial input. Yeah. So this is this diagram, which is a mixed diagram. So this is what I call it as 2. 2 boxes in the first row. Yeah, Young diagram. So if you take a tensor product, this is what I am saying. If you take the tensor product of 2 such diagrams, okay, what will happen is that there is a diagram which appears twice. This is the first property which we are all familiar. When we do octets, we know that it comes more than once. This is what we call it as multiplicity. This does not happen for symmetric. Symmetric tensors, every representation occurs only once. Is that right? When you take tensor product of 2 spin half or spin 1 or SUN symmetric, you will always get every irreducible representation to occur only once. But once you go to this octet kind of diagram, you do see that some representations occur more than once. This is for any general SUN. Yeah, okay. So 4 2 I mean this one. Okay. Yeah, so there is a slight notation which I probably, let me not confuse right now. For the time being, you take it to be this one. But there is a way in which if you take R cross R bar, then the diagram becomes too messy. So we take a midpoint which is 0 and then we try to rewrite. Okay. So for R cross R, you don't need that semicolon. Yeah.
What is that number after the bracket?
Yeah, this just to say that this is like a degeneracy.
Oh, I see. This is labeling the.
Yeah. It appears twice, and I'm going to put additional label to take care that even though it appears twice, I will call it as two distinct primary fields. This information is the additional information which forced us to 3 1 cube is like this. Yeah, 3 and then you have a 1 1 1 1 1. Yeah. Is that okay? So 2 cube will be, this is 2 cube. The semicolon 0 you can forget for the time being. But there is, if you take R cross R bar, then that becomes very.
So if we take SU3 for example, we won't see the degeneracy actually, because we cannot have 3 rows.
No, you cannot have 3 rows. That is another way of saying it. But diagram wise, it will be there. This is singlet. This will appear again. This will again appear. This is singlet. Right?
So for small rank, things will decompose further into big.
No, the appropriate diagrams will, whether it's legal or illegal, will get out. Like SU2 if you are doing, it will be like doing 2 spin half. Right? Most of the other representations will not be allowed also, right? This diagram will not
If
be.
we do SU2,
Yeah,
then
this.
on the right hand side there is no degeneration.
I get. So n equal to, if you put the rank n equal to 2, SUN with n equal to 2, then mutant should not be distinguished. Another way of writing is you write the polynomial in variable a which is 2 to the n and substitute n equal to 2 and see whether those two mutant pairs share the same polynomial. That's a check. Yeah, good. So the only thing is when I wrote this 4-point conformal block, now I will give these two composition will also have one more index corresponding to the subscript that I'll call it as R3, R4, R1. This plays a lot of work, you know. This gives us that mutants is not, the mutant operation is not an identity operation. This additional index is like lifting the degeneracy. So this was crucial. And this is the point which we missed because we always looked at this diagram, we wrote the eigenvalues which depends on the diagram, but we have to also take care that it depends on the subscript R.
So just to follow up on this,
Yeah.
so if I take SU3,
Yeah.
then this 3 to 1 guy should appear like 2 comma 1
2 comma 1 and it will appear twice.
and it will appear twice.
Yeah.
So SU3 will do. So I don't need to
Yeah.
go to
So
higher this.
that is one way of saying, but there is one more theorem that which we all follow, that whenever we work out symmetric, okay, if we work out the symmetric, we have the polynomial in variable a and q, where a is q to the n. Okay, I can take this answer and write out for the conjugate, which is, I just make this into antisymmetry. When I do that, this polynomial with this representation will be replace q by q inverse. So this is what we call it as, in the knot theory language they call it as mirror symmetry, where the polynomial for this you don't need to work it out, whatever is this polynomial, take the a variable but put this to be q inverse. Okay. argument if I take this, okay, this when I do the row column interchange, it is the same. The row becomes column, column becomes row, it's the same. So this operation is also not seen by mutation. So that is why SU3 will not do. This is another way of saying it. This was Morton's proof, that Morton showed that symmetric cannot distinguish mutation. The row column interchange of a diagram will not interchange mutation. If you want to take this diagram, you please go to SU4 at least, is what it is. Yeah.
The invariants will be related to colored source from
Yeah, colored home fly.
colored one.
Yeah, SUN. SU2 doesn't distinguish, so there's no point. Yeah. Okay. Okay. So the formal way is how to see it diagrammatically, the two tangles which are mutants along x direction, is that you add a B1 and a B3 inverse. You can diagrammatically do this Reed-Master move 1, 2 or 3. You can make it look like this. Similarly, here you can flip it by adding these following braids. Okay. So what do we have to do? We have to show that this state is non-trivial, and similarly this braiding state is non-trivial. Or equivalently, you have to write the state for this involving B1, D1 inverse, and now we have an additional, not only the representation, but I have to also keep track of the additional symbol for the multiplicity. And then this gives us, when R1 is not, this is all signs, but when R1 is not equal to R2, we do get a non-trivial. It will not be an identity matrix. So this is the first step which showed that mutation, there is a possibility for mutation to be distinguished. Okay.
On this diagram, what is the 2 point?
Which 2 point? No, no. No, I have to write two tangle state in one frame. When I am doing it in that frame, one is an identity operation if you don't do any mutation, and if you do a mutation, there is some signs on some of the states. So it cannot be written as just a tensor product of two states. It's not possible. Okay. So this is what we elaborated, and this for all the polishing way in which we wrote after referees, arguments and so on. So it came out as a consequence here. So parenthesis is what gives you signs, and the amplitudes. These are this is what I take the inner product with the basis, and these amplitudes are related by sign when R1 is not equal to R2. Okay. So that's the first step occurs, and clearly this R1 index wouldn't have come into picture if you don't have irreps with multiplicity.
So now we are coming close to the real world.
Yes. So okay. So let me put a cutoff after this. One more slide, I think, this and that. So this is formally, you can write any state with an F tangle this way and the mutant of this tangle this way, and then we can show by the previous step which I wrote how this F is related to F by additional braiding. I can relate the coefficients. Okay. So once I have these coefficients, I can formally find what is the difference between these two. I don't care about the other piece which I have to glue with this. Right? So formally I know that this will be not an identity state, and it is going to give me something non-trivial. It depends on the tangle and looks at only the multiplicity sector. Okay? The 3 to 1 if it is parallel, and then this 1 comma 1 is for the R cross R bar. So this is the one which gives me non-zero answers, and this is what we have verified for, and you can glue it with the other one, so the difference is non-trivial, and we redrew the same diagram as an F tangle and G tangle, and then we wrote out this explicitly in terms of the Raka matrices. Now the Raka matrices will have R1, R2, R3, R4 elaborately, and then we show that the invariant is. So that is the point where I could stop, and let me just end by saying that knots are of two types. In fact, even up to 10 crossings, you do see there are many knots which I cannot draw like a Feynman diagram like diagram, and we need other methods too. So aim of our work has been that at least in the website we would like to update polynomials up to 12 crossings.
Notebook.
Not e-book. Okay. So this website is alive. You can go and check. Suppose somebody wants a knot invariant for a specific knot, they can go and get it for whichever representation they want. So the thing is, it is becoming tedious for non-arborescent knots. Still,
Like a Feynman diagram with loops or not Feynman diagram?
you can treat it like that. They cannot be drawn like the building blocks which I showed. So this is looking very difficult, but there are other methods which we are exploring. At least for lower number of strands, we have some handle. I don't know, till 10 crossing has it been done? We have finished till 10 crossings. But we are aiming to go up to, so this is funded by DST and RFVR. And integer coefficient, let me stop and I give a later an elaborate talk. Let me go to the conclusion. Yeah, so essentially at the end of the day, I hope I have made you get a hands-on feeling on how you could work out knot invariants. Knot invariants are in terms of braiding eigenvalues and duality matrices, and you can work out the putting symmetric, because I have the duality matrices, the explicit expressions for arborescent knots, we could work it out. For mixed representation, other than 2-1, where the Raka matrix was available, we still don't know for representations like, something like this. We don't know how to write the Raka matrix. If we have some idea, then it will help us to write for any arborescent knot, any mixed representation. If we could do it, it will be nice. That's still an open question. Right now, we have found some interesting results, just like the way we did it for symmetric, at least for rectangular representation. So this is what I call it as n comma n. The beauty of these representations, again tensor product, there will be no multiplicity. So these are also multiplicity free representations. So there is some ongoing work where we are trying to do, and right now it is available up to 10 crossings by other methods and so on, and it is updated in the knotebook.org. And hoping that we will get some computational handle on what Witten is saying, and also relation. This is something which I didn't talk. There are connections to Seiberg-Witten curves, to A polynomials and so on, but it's still under investigation. Let me stop here. Yeah. Thank you.
Any questions from ICTS?
Yeah, so what is the main technical complexity in calculating these regular 6J symbols, extending this Joker work to
Yeah, Joker is also very tedious. That method should be possible. It will be still tedious. We have been trying to do this for 3,1, and it has been a very tedious exercise. We have not completed. Even 2,1 I think it was huge, since it's the first non-trivial mixed representation, and in principle it is possible. It gets tedious to get the form. Ideally, what I would like to do is, like, we should get a closed form expression. Like Jokers have got the 10 cross 10 matrix elements explicitly. But it should be nicer if we can write it in terms of as a functions of representations which are there, ATS, functions of representation, TS, and also those mixed representations. That kind of expression would help us for higher dimensions, because you know the number of irrefs will keep increasing. 10 cross 10 will become probably 14 cross 14 and so on. It becomes tedious. That's why we are resorting to other methods of getting the 3,1 invariants. Yeah.
But is this an algorithmic thing which can be, let's say, put in computer or something? It's just
I think
it still requires some amount of proving part which cannot be easily.
I think some bit of us trying to simplify, and then maybe it can be put in the computer. But right now, I don't think it can be mechanically put, and you can extract the answers. Doesn't look like that.
Okay, another question. So, are there knots which are known to be distinct, but which cannot be deformed each other, but which are not distinguished by any, even a general colored home fly?
So up to now, up to 10 crossings, I think our colored home fly PT is able to do a good job.
Mm-hmm.
And mutants are not there in this up to 10 crossings. Okay. Beyond 10 crossings, from 11 crossings, there are mutants. This is not the only mutant. There are pretzel type of mutants which we are still not able to distinguish with our 2,1. Okay. We need to go to other.
Theorem that wasn't proved that Chern-Simons can never distinguish.
No, I don't think so. We cannot prove this way or that way. We can at least check data. Yeah. So there are beyond 10, I think we have not compiled all the 12 crossings to make, at least for situations which are not related by mutation, to make this statement. Things which are related by mutation, not all mutants have been distinguished. So it's still classification beyond 10 crossings still has not been achieved. One of the barriers is if we do arbitrary mixed representation, most probably they will distinguish is the hope. And we could get this explicit data up to 12 crossings at least.
But is there some result that, if you can distinguish up to some crossings? I don't know, like some.
Up to 10 crossings we have distinguished using our Chern-Simons colored home fly PT.
No, so what I was asking was, is there some result, let's say if you distinguish all up to 20 crossings, then you can distinguish anything?
That is not visible to us, but if we write a family invariant, maybe we can see that if you change the parameters there, if it gives you an equivalent knot, that family invariant is same, but if it is giving you an inequivalent knot, the invariant is different. Can we randomizely check that?